So this problem has us calculate a capacitance and then compare the energy stored in the capacitor to the energy stored in the electric field throughout space. So the capacitor is a solid conducting sphere. That's one of the pieces of the capacitor, one of the conductors. The other conductor, here's the hint, part A, treat this sphere as one capacitor plate. That's the conducting sphere. Another sphere, another conductor with the same center and an infinite radius. So we put a charge, say a charge plus Q, on this solid conducting sphere of radius r. The minus Q is out at infinity, and so there's an electric field in between. The capacitance is what we're looking for first. How do we find the capacitance? Well, what we need for the capacitance is the voltage difference between the two conductors, because we're going to take the capacitance is the charge divided by the voltage difference. So we did talk about this a lot in lecture. Basically, because this is a solid conducting sphere, the charge spreads out. We can use Gauss's law for this, for what ends up being a spherically symmetric charge distribution. And Gauss's law is going to show us that the electric field outside this conductor of radius r, and also the electric potential field outside this conductor of radius r, is exactly the same as the electric field and the electric potential field of a point charge with the same total charge as the conductor located at the sphere's center. So this doesn't say that the electric field is the same everywhere in space for the point charge as it is for the sphere, the conducting sphere, just the same outside the conducting sphere radius r. When you're outside that radius, then the electric field is outside there is the same as the electric field of a point charge if you were that distance away, r or farther away, capital R or farther. So if it's just like a point charge, then the voltage is Q over 4 pi E0 R at the surface of the sphere. So that is the electric potential of one of the conductors of our capacitor. This is referenced already to 0, because it's the voltage of a point charge. This is referenced to V equals 0 for R equals infinity. And so we automatically have our sphere at R equals infinity at 0 volts. So the difference between the two, the difference in voltage between the conducting sphere and the sphere at infinity is in fact just this voltage. So the capacitance is Q over delta V. Delta V, as I said, is just Q over 4 pi E0 R. Take Q and divide by that. I just get 4 pi epsilon 0 times capital R. The energy stored is 1/2 C times delta V squared. So Q squared over 8 pi E0 capital R is the energy stored with charge Q in this capacitor. And this is the energy stored is what we need to compare the integration of the field energy density. So there's the energy stored in the capacitor. The density of the field energy, that just means the energy per unit volume. The book shows you that this is 1/2 epsilon 0, or at least it argues that it's 1/2 epsilon 0 times the electric field squared. So the electric field is just like the electric field of a point charge, which means it gets smaller and smaller as you go farther away. So the energy density is actually getting smaller and smaller as you get farther away. We're going to need to find the total energy. And that means we have to integrate the energy density over the total volume. Now, the total volume, of course, is the volume from this sphere of radius r, where the electric field starts, out to the sphere of radius infinity. So it's a big volume. It's an infinite volume. The way you find the energy that you need to integrate is that the energy is the energy per volume times a volume. So a differential energy is the energy density, this energy per volume is the energy density, times a differential volume. Because this energy density depends on the electric field, and the electric field depends on R, the distance from the center of the sphere, this dV, this differential volume, is best written as something that depends on R, and in spherical polar coordinates you can get something like, because the integration over the angle variables gives you 4 pi, and the rest of dV is r squared dr. So 4 pi r squared is a surface area of a sphere that's radius r, and dr is the thickness that makes this a differential volume of a shell of thickness dr at radius r. And then E depends on 1 over r squared, so we need to take this, to get the energy per unit volume, we need to multiply 1/2 E0, and then square E, multiply by the differential volume, integrate it over the entire volume where there's an electric field. The electric field starts at R, starts at the surface of the conductor, because that's charged, runs all the way out to infinity because the other conductor is out at infinity. So here's the energy density, 1/2 E0 times E squared. Here's dV. Integrate that from R to infinity, end up with Q squared over 8 pi E0R, the same as the energy stored in the capacitor.